all. Welcome you all. Myself Nagarajan, Assistant Professor in EC Department, Rohini College of Engineering and Technology. In this video, let me see about the embedded system and IOMT subject for biomedical engineers. Topic is here A to D and D to A interfacing. That is analog to digital and digital to analog interfacing. So first let us see the introduction of A to D and D to A converters. In this converters, let us define the basic definition. What is ADC? What is DAC? Okay. First of all, we want to define that is the ADC. So analog to digital converter is a device that converts analog signal into digital signal. So that can be processed by a microcontroller or digital system. So analog to digital converter means it is a device that converts analog signal to digital signals that can be processed by a microcontroller. So next, digital to analog converter definition. So it is also a device that converts digital signals back into analog form, allowing digital system to interact with the physical world through actuators, audio system or other analog outputs. Now let us see the importance in embedded system. So in a embedded system, why we are using a ADC and DAC. So in ADC enables the microcontroller to interface with the real world by converting sensor data into digital form for processing, storage and decision making. So for DAC, digital to analog converter, so it is will be allows the embedded system to produce analog output from digital data, crucial for applications such as the audio signal generation, motor control and instrumentation. Now let us see the one by one, that is the analog to digital conversion. What are the basic principles behind in this analog to digital converter? So working principle, first one is a sampling. So sampling is nothing but it is a continuous analog signal is sampled at a regular interval to create a discrete time data point. The rate at which this sampling occurs is known as the sampling rate. Next one is a quantization. So quantization, each sampled value is then approximated to the nearest value in the set of discrete level defined by the resolution of the ADC. For example, 8-bit, 10-bit, 12-bit ADC. In higher resolutions provides more accurate representation of the analog signal. Next one is a encoding. So the quantized value is encoded into binary format that the microcontroller can process. So this is the basic working principle behind the analog to digital converter. First one is a sampling, then quantization, and after that encoding. Now let us see the what are the key parameters used in analog to digital converters. First one is a resolution. So resolution is nothing but the number of bits used to represent the analog input. So number of bits used to represent the analog input. Higher resolution allows for finer granularity in the digital representation of the analog signal. For example, a 12-bit ADC can represent 4096 different level. Next one is a sampling rate. So the frequency at which the analog signal is sampled, higher sampling rates capture more detail from the analog signal but require more processing power and storage. And next one is the accuracy and linearity. So measures how closely the digital output matches the actual analog input. Non-linearity and error like offset, gain and noise can affect accuracy. The next one is a input range. The ranges of analog input voltage that the ADC can accurately convert inputs outside this range can lead to saturation or clipping. Now let us see the type of a analog to digital converters. First type is a successive approximation register. A SAR ADC. So it is uses a binary search algorithm to converge on the input signal. SAR ADC are commonly used due to their good balance between speed, accuracy and power consumption. And next type is a delta sigma ADC. So delta sigma ADC uses a oversampling and noise shaping to achieve high resolution and accuracy. Delta sigma ADC are used in high precision applications such as audio recording and instrumentation. The next type is a flash ADC, the fastest type of ADC using parallel comparators to convert the signal in a single step. So flash ADC are used in applications requiring extremely high speed such as a digital oscilloscope, but are limited by their higher power consumption and lower resolution. Next one is a pipeline ADC. So combines features of SAR and flash ADC to achieve a good trade-off between speed, resolution and power efficiency. So often used in high-speed data acquisition system. Now let us see the DAC, that is a digital to analog conversion. So what are the basic principles behind the DAC? First one is a binary weighted conversion. So the digital input is converted into an analog output by assigning each bit a corresponding voltage level. So the DAC add up these weighted voltage to produce the final output. Next, resistor ladder network. A common technique used in DAC where resistors are arranged in a ladder configuration to generate the required analog voltage from the digital input. The next one is a output smoothing. The output of a DAC often requires smoothing to eliminate steps and produce a continuous analog signal. Next, what are the key parameters used in DAC? So first one is a resolution. So resolution, the number of bits used in the digital input, higher resolution DAC can produce more precise analog output voltage. Next one is a settling time. The time taken by the DAC output reach its final value after a change in the digital input. So faster settling times are important in application requires high speed update. Next, linearity. So the degree to which the output analog signal is proportional to the input digital code. So non-linearity can introduce distortion in the output signal. Next one is a output range. The range of voltage that the DAC can produce. Some DAC provide a rail to rail output or covering the entire supply voltage range. Next, let us see the types of a DAC. So first one is a binary weighted resistor DAC. So it is uses a resistor with the binary weighted values to produce the analog output. This type is simple and fast. Next one is a R2R ladder DAC. So a popular and cost-effective DAC design that uses resistor of only two values. One is a R and another one is a 2R to create the analog output. The R2R ladder DAC is widely used due to its simplicity and scalability. The next application types is a Sigma Delta DAC. So similar to Sigma ADC, these DAC oversample the input and use noise shaping to achieve higher resolution output commonly used in audio applications. I hope that all of you understood about the analog to digital and digital to analog interfacing. In this analog to digital and digital to analog interfacing, we define what is ADC, what is DAC, what is the importance in embedded system, why we are using ADC and DAC circuits in embedded system, what are the working principle behind in the ADC and as well as the DAC. Thank you.